Imagine you are standing in the middle of a vast, frozen lake at night. The ice beneath your feet stretches in every direction, not perfectly flat, but close enough that you can see for miles along the surface. Stars above, silence, and then you notice something strange. Every light on the horizon is moving, not toward you, away from you. Every single one. You turn slowly, checking all directions, and it is the same story in every quarter. Everything is leaving. You are at the center of a quiet, creeping exodus, and you have no idea why. The ice seems solid, the night seems calm, but something in the geometry of this place, something in the hidden structure of the ground beneath your feet, is pushing everything away. You can feel that you are not standing in random space. You are standing on something. Something immense and invisible that has been shaping the world around you for longer than human civilization has existed. You just didn't know it was there. We have spent almost a century believing we understood our address in the universe. The Milky Way sits inside the local group, a cluster of galaxies held together by gravity, anchored by two giants, our own galaxy and Andromeda. Around them orbit dozens of smaller, fainter companions. And beyond that neighborhood, the universe expands outward in all directions, carrying galaxies with it like raisins in a rising loaf of bread. Edwin Hubble established this picture in the 1920s, and it became one of the cornerstones of modern cosmology. The universe is expanding, and nearly everything is moving away from us. That much we knew. But here is what never quite fit. The galaxies just outside our local group, the ones close enough that the combined gravity of the Milky Way and Andromeda should be hauling them inward, are moving away from us anyway. They have been doing this for as long as we have been measuring them. For 50 years, scientists tried to explain it. They tweaked their mass estimates, adjusted their models, ran simulations after simulation. Nothing worked. The local group is massive enough, on the order of trillions of solar masses, that by all rights, it should be exerting a noticeable gravitational grip on its nearest neighbors. Instead, those neighbors are drifting outward in an eerily quiet, orderly flow, as if the local group's gravity simply does not reach them. That's either a profound failure of our models or a sign that something else is going on entirely. In January 2026, a team of researchers led by PhD graduate Ewout Wempe at the Kaptein Astronomical Institute in Groningen, the Netherlands, working alongside Professor Amina Helmi and collaborators from Germany, France, and Sweden, published their findings in Nature Astronomy. They had finally solved the 50-year mystery, and the answer reshaped the way we understand where we live. We are not floating freely in space. We are embedded in a structure, a vast, flat, invisible sheet of dark matter stretching 30 million light-years in every direction. Picture a pancake the size of a small universe, and we are the blueberry pressed into its center. To understand what Wempe and his colleagues actually found, you have to understand the method they used, because it is, in its own way, as remarkable as the discovery itself. They did not point a telescope at this structure and photograph it. You cannot photograph dark matter. It emits no light, absorbs no light, reflects nothing. The only way to infer where dark matter sits is to watch what gravity does to the things you can see. So, instead of looking outward, they started from the beginning. The team used the faint afterglow of the Big Bang, the cosmic microwave background, as their starting point. That ancient signal, filling the entire sky at a temperature just barely above absolute zero, encodes the earliest density fluctuations in the universe, the tiny seeds from which every galaxy, every cluster, every filament of the cosmic web eventually grew. Using a computational method called Borg-Bayesian origin reconstruction from galaxies, they fed those early conditions into a powerful computer and let the universe evolve forward in time, not once, not 10 times, but 169 separate times, each with slightly different starting parameters. Each simulation had one goal: reproduce the exact situation we see today, the mass of the Milky Way, the mass of Andromeda, the position and velocity of Andromeda as it moves toward us at around 110 kilometers per second, fast enough to cross the distance from Earth to the Moon in just over an hour. And critically, the positions and velocities of 31 relatively isolated galaxies just beyond the local group, galaxies that have been measured and tracked over decades in large-scale surveys. Out of the 169 simulations, those that successfully matched all of these conditions had one feature in common, every single one of them. The matter surrounding the local group was not arranged in a sphere. It was arranged in a sheet. But that's not the most unsettling part. The sheet isn't just flat. It is structured in a way that creates a gravitational environment unlike anything our previous models assumed. At the center, where the Milky Way and Andromeda sit, the density is roughly twice the cosmic average. But as you move outward along the plane of the sheet while staying within it, the density actually rises. The sheet contains more and more mass further from the center, out to distances of about 30 million light-years. And above and below the sheet? Almost nothing. The simulations revealed two colossal voids sandwiching the entire structure, regions where matter density drops to somewhere between 5 and 10% of the cosmic mean, for all practical purposes, empty. Vast, abyssal, almost unimaginable emptiness pressing against the top and bottom of a dark matter pancake that holds entire galaxies like fossils in amber. Think about that geometry for a moment. If you are standing inside the sheet as we are, gravity is pulling you in every direction along the plane, and from the distant edges of the sheet, additional mass is pulling outward. For the galaxies just outside the local group, but still roughly within the plane, the local group's inward gravitational pull is almost perfectly cancelled by the mass of the sheet further out. They feel no net inward tug. They are free to drift with the general expansion of the universe, undisturbed. And above and below, where you might expect matter to be falling inward, toward us, there is almost nothing to fall. The voids are real. Astronomers had already catalogued the local void and noted its strange emptiness, but no one had connected these pieces into a coherent picture before. The sheet explains three things at once, which in science is a sign you may have found something real. It explains the local sheet, the flat arrangement of nearby galaxies that astronomers had noticed for decades without fully understanding. It explains the local void and why our galaxy appears to be moving away from it at around 260 kilometers per second in the direction of the supergalactic plane. And it explains the quiet Hubble flow, the mysteriously smooth, orderly recession of galaxies around us that had long defied reconciliation with the massive gravitational presence of the Milky Way and Andromeda. And then the simulation found something else. When the team added up the total mass implied by this sheet-like arrangement, the numbers came back larger than anyone expected. The local group itself, Milky Way, Andromeda, and their satellite galaxies, clocks in at roughly 3.3 trillion solar masses. That is a number so large, it has lost all meaning in words. So try this. If you could somehow weigh our entire sun, a ball of plasma, 2 million kilometers wide, so large it could contain more than 1 million Earths, and then multiply that mass 3.3 trillion times, you'd have the local group. And yet that mass, extraordinary as it is, represents only a fraction of the gravitational influence at play here. The sheet contains more than 4 times that amount within just the nearest 13 million light-years. The full structure, dark matter and all, is something our models had no room for. Traditional spherical models of the local group's mass distribution fail to reproduce the observed galaxy velocities when you account for this much matter. Only the sheet model fits. Professor Helmy, who co-led the research and has spent decades studying the dynamics of galaxies in the local universe, put it plainly in the paper's announcement. I am excited to see that, based purely on the motions of galaxies, we can determine a mass distribution that corresponds to the positions of galaxies within and just outside the local group. That last part deserves emphasis. They did not build the model to fit the structure. They inferred the structure from the motions, and then found that the structure they uncovered already existed in the data. The cosmic web had been telling us this for years. We just hadn't learned to listen. Here's where it gets truly strange. Dark matter makes up approximately 85% of all matter in the universe. Everything we can see, every star, every planet, every galaxy, every nebula, every atom of gas drifting between the stars accounts for only 15%. The remaining 85% is invisible, interacting with nothing we know how to detect except through gravity. And yet, it is this invisible substance that built the scaffolding of the cosmos. The cosmic web, the vast network of filaments, sheets, and voids that structures the universe on the largest scales, is fundamentally a dark matter architecture. Galaxies do not create the web. They trace it. They accumulate where dark matter has already gathered, lighting up the framework like cities along an ancient trade route. We have known this in a general sense for some time. But what Wempe's team discovered is that this architecture exists not just at the level of galaxy superclusters, structures spanning hundreds of millions of light years, but right here, at home, in our own cosmic backyard. The sheet they found extends to roughly 30 million light years. That is enormous. The distance from Earth to the Moon is just over a second at the speed of light. The distance to the nearest star is about 4 years. The distance to the center of our own galaxy is 26,000 years. 30 million light years. The length of this dark matter sheet is roughly 1,200 times the diameter of the entire Milky Way. It is a structure so large that the Milky Way itself, all 100,000 light years of it, is essentially a point on the map. We are embedded in something we cannot see, cannot touch, and cannot escape. And the simulation found it not by looking for it, but by running the math until the universe had no other choice but to reveal it. There are caveats worth sitting with honestly. The sheet is inferred from computer simulations, not directly observed. The 169 virtual universes that Wempe's team ran all converged on this shape. But a simulation is still a model, still dependent on assumptions about the physics of dark matter, the accuracy of the starting conditions drawn from the cosmic microwave background, and the completeness of the galaxy velocity data from surveys like the Cosmic Flows catalog. The team acknowledges that the model is limited by current observational coverage. They predict a specific observational test. If astronomers find more distant galaxies above and below the sheet's plane, moving rapidly inward, perpendicular to the sheet, it would strongly confirm the picture. That observation has not yet been made. But the paper was published in Nature Astronomy, one of the most rigorous journals in astrophysics, in January 2026. Astronomer Amina Helmi, one of the most respected voices in Milky Way dynamics, stands behind the results. And the fact that the simulations reproduce not just the galaxy velocities, but also the large-scale structure of the local supercluster without being told to do so, gives the model a striking predictive credibility. The universe seems to be telling us that our assumptions about where we sit have been incomplete. And here's the thing that stays with you after the math is done and the papers are set aside. Human beings have always sought to understand their place. The ancient Greeks put Earth at the center of everything. Copernicus moved us to the edge of something vast. Hubble showed us that our galaxy is one of billions, adrift in an ocean of expansion. Cosmologists in the 20th century gave us the cosmic web, the idea that galaxies are arranged along dark matter filaments the way morning dew clings to a spider's web. And now, in January 2026, a PhD graduate at a Dutch university ran 169 simulations of the universe and discovered that we are embedded in a sheet. A flat, invisible wall of dark matter stretching 30 million light years in every direction, not floating freely, not at a random position in a uniform halo. Pressed into a plane, flanked by emptiness so profound, it alters the gravitational destiny of every nearby galaxy. There's something quietly humbling in that. For 50 years, we watched our neighbors drifting away and couldn't understand why they weren't drawn to us. We assumed the problem was in our mass estimates, our measurements, our models. It never occurred to us that the answer was structural, that we were sitting in a geometry we had never imagined, a geometry whose shape was itself the explanation. The universe was not misbehaving. We had simply misread the address. We are not at the center of anything. We are not at the edge of anything. We are embedded in a sheet, sandwiched between voids, held in place by dark matter we cannot see, and shaped by forces whose full architecture we are only beginning to map. And somehow, against all of that scale and strangeness, a small group of humans sat down with some equations, some satellite data, and a very fast computer and figured it out. That's either terrifying or magnificent. Possibly both. Thanks for watching, and I'll see you in the next one.